right. Any other random questions? I enjoy talking about sabotage.
We'll do the first medical
Did
treatment.
you get this one?
Ooh,
What was the question?
what would be the first magical trinket I would create? All right, so it's tempting to say one that, you know, would let me travel through time, but I'd rather not invent that lest anyone else find it, frankly. One of the shows that I watched as a kid had a very cool way of teleporting, basically. And the artifact in question was called the Golden Tiger Claws. It was just a gauntlet you wore with 3 metal spikes on it, and when you slash with the gauntlet, it just tears open a wormhole that you step through. Good, cool, non-problematic transport over the entire planet. You just visualize where, and the wormhole takes you there. The second one I would invent is one that stops time, but doesn't let me travel through it. And then flight.
Would you put these like magical trinkets and something onto trinket, or would you make like a wooden pencil, a magical trinket, sometimes fly?
Maybe. I've thought about making something that I could pass out that just like makes the wearer healthy and just distribute them on the mass scale. Eliminate the need for anyone to get sick. Anyway, this is the stuff that I think about late at night. How are you guys?
Good.
Where's my mouse cursor? I do encourage these goofy lines of inquiry. It makes my day better. In a vague attempt to get on track, please do ask more movie stuff later. Today is Friday, October 5th, and the Chapter 6 homework and quiz is currently due on midnight at the end of Monday. So please be working on those and come to class on Monday with any questions you have. Additionally, my goal is to try to have the tests graded and ready to hand back to everyone on that Monday. If that is the case, then we'll spend some time looking over them, and I am uploading the answer key so that you can check back and use it for studying purposes. Because I have so many tests, it would take me eons to actually write in comments as to what you should have done for every single question for every single person. So instead, I'm just marking them wrong, marking the points that you missed, and then you can check the key for what actually should have happened. Because, again, if I wrote them all on everyone's tests, I'd be doing it till the heat death of the universe. Sorry, guys. Additionally, next week will be a normal week, all lectures, all lab days, report as normal. And next week we should continue in and conclude Chapter 7 is my goal. Today we'll continue looking at rotation. We're going to finish the example we started last time, and then we're going to look at a different one. I want to work at least these 2 examples to completion before we introduce any new rotational concepts, because this point in the course is always kind of a weird sticking point because no one has thought about things in terms of rotation until this point in their lives, probably. So we're going to take today to keep working through that, make sure they settle nicely for you guys, and then next week we'll introduce new rotational concepts. Any questions before we get started?
Does that mean Chapter 7 homework is going to do on next Friday?
Good question. I'm probably going to make Chapter 7 homework due the Monday after next. So my goal is by the end of today, I'll have it up and scheduled for the end of Monday the 15th. And try to move us towards about 1 a week. That's my goal, at least. Other questions? All right. So, I believe last time we left off with this specific car. We are told that the driver of this car is initially driving forward to 20 meters per second until they hit the brake and begin decelerating at a rate of negative 1.75 meters per second squared. We know the radius of all of the tires, and we also know that as the car slows down, it's still going to drift some distance forward, As it drifts forward, its wheels will still be spinning, so they will have their own angular velocity, their own angular acceleration as they're slowing down. And since they're still spinning, they'll still be racking up some number of radians rotated. We calculated that number of radians. Please correct me if I'm wrong. I believe that was 728. Cool. 0.6. I'm only remembering it because I've done this example 2 other times this morning. 128.1.
I think it was 0.1.
All right, thank you guys. So that's in units of radians. This is an idea of the number of times the wheel spun as this process took place. As a reminder, 2 pi radians correlates to 1 rotation. So if we divided that number by 2 pi, it would tell us just literally the number of times the wheel spun as it slowed down. As it stands, we have this. It's a pretty significant number of radians. And lost my train of thought for a second there. My apologies. With this information, we now have a different question on our hands. We know that the car is going to drift forwards. We know that as it slows down, its velocity is going to incrementally change from 29 down to 0. What we're being asked now for the second question of this example is, as this car is slowing down, as it has moved forwards half of the total distance that it will roll, what will its velocity be, what will the angular speed of the wheels be at that moment in time where we move forward half of that distance? So we're halfway through slowing down. We want to know what the angular speed is at that moment. Pardon me. So, what we're after is a very specific final angular velocity. I'm going to label it final omega, but I'm going to further specify omega final 1/2. Because when we start looking at formulas in a second, the variable we're looking for will be omega final. It's just this is a specific moment in time, not the very last moment when the car stops. It's a moment in the middle. So omega final is what we're after, a specific omega final. And we need to get there. Now, I believe I mentioned this before. With a lot of these linear and rotational examples, there's going to be 2 paths we can take. We can operate entirely in the linear world and then convert to angular. Alternatively, we can convert everything at the start into angular and then operate in the angular world. And both will get us where we want to go. So we will get there no matter what. It's just a question of, do you want to go through the field of flowers or do you want to go up by the creek? For this specific case, we are after omega final, a specific omega final. And to help us get there, we have theta, or rather the full theta. This would not be what we actually plug in for a delta theta to find this number, because at the point in time we're looking at here, half of this theta would have elapsed. We would have only spun half as much at this point as we would at the end. So we would actually literally want to cut this number in half if we were ever to try to use it. And I believe that would be approximately 364. 5, rad. So we do now actually know the delta theta for the specific point in time that we are looking at. We also know tire radius, linear acceleration during this whole process, and linear starting velocity before we actually started slowing down. So we're kind of stuck between worlds right now. We've got some linear stuff, some angular stuff, and we just have to pick which world we want to work in at the start. Now, my personal vote, which only matters because I'm the one up here holding the markers, is if we were to work in the linear world and then convert linear final velocity into angular velocity, in order to get there, we would still need to convert this into linear first, and then our linear answer would need to convert into an angular answer. Meanwhile, if we convert our linear stuff into angular stuff, we can work entirely in the angular world. So I think it's 2 conversions either direction, but for some reason, converting linear to angular at the beginning feels better to me. You're allowed to disagree.
So is it fine if we actually try to figure out time and use it to figure out the,
You absolutely could. You could figure out time first if you wanted to. You want to use that.
because since time is not gonna be converted to either, because it's just a 1 unit thing.
You're right. There is no difference between time in either linear or rotational, because kind of like how it's the same time whether you're flying sideways or falling, it's the same time whether you're moving forwards or spinning. There's no angular counterpart to time, mercifully. So you could do that, yes. If you prefer that route, you can take it. For some reason in my head, the conversion followed by one formula seems to be simpler, because if we convert everything, we can get there with one formula and not having to find the time. If we specifically employ formula 4. Because if we convert our initial velocity and our acceleration, we know theta, and we're after final. So, at least in my head, converting and then using one formula seems like the least amount of work. You're allowed to disagree. There's multiple ways to get to correct answers in this class.
So does that mean we're not gonna have the same time? It's gonna be a different time?
Well, the time, okay, if you were to try to find the total time for slowing down and cut that in half, that wouldn't work.
Okay.
Because when you're slowing down, when this car slows down, you're going fastest at the beginning. So at the beginning, you're covering a lot of ground. But then at the end, you're covering less ground. So the answer we're ultimately going to find is, I know from having done this before, that the linear velocity at that halfway point is like 21 meters per second. The velocity hasn't even been reduced by half yet. It's gonna just keep getting incrementally, not really exponentially, but it's moving so fast at the beginning that half the time is not spent by the time you reach half the distance. You reach half the distance long before you reach half the time. So I prefer operating with this. You could absolutely find the time it would take to move this distance, and then that would be the time you plug in to find omega final. So you can do that. I just think that doing it this way is fewer steps. You're allowed to disagree though. So I've been talking about doing it this way. Let's actually show that process now. I'm going to recommend the angular version of Formula 4. We already know our half point delta theta. We want our half point omega final. We would need angular velocity initial and angular acceleration. We know the linear versions, so we can just convert them over. And we can perform that task with these nice conversion formulas we have right here, we're ultimately going to end up dividing both numbers by our radius. So 29 divided by 0.33, I believe, from my recollection, comes out to about 87.88 rad per second. And negative 1.75 divided by 0.33, I believe comes out to about negative 5.7 rad per second squared. Does anyone's math disagree? 5.3, thank you. My memory is flawed and so is my mental math skills. We agree with these? Okay. So we now have all the angular stuff that we need to work this version of the formula. So omega f, for the specific point in time we're investigating, will be omega initial squared, so that'll be our newly converted 88.78 squared, plus 2 times our newly converted angular acceleration. We need to keep the negative, that is important. And then times our halfway delta theta. I'm going to show another line of the algebra on my calculator. Eighty-eight squared should be approximately 7,881.9, and then 2 times negative 5.3 times 364.05 should be approximately negative 3,858.93. Negative is important, and the whole right side should be under a square root. We need to take the square root of both sides to get omega f by itself. I'm beginning to wonder if I actually do have, I've been calling it dyslexia of the mouth, where the wrong word just comes out sometimes. I think I looked that up. Is that dyslalia? Dyslalia. Anyway, that's a question for me to research later. So for our final answer, what are we getting?
62.
Approximately, I've got, using what I've got on the board here, approximately 63.43 rad per second. I'd say 62 is reasonable given rounding. I want to check that. No. So that is specifically our halfway point omega final. If you wanted to check and convert that into linear to compare it to our initial linear velocity, then you would want to multiply by 0.3, and then I think should come out to about 21. But we can also compare it to our initial angular velocity, excuse me. Notice that we're only about a fourth of the way slowed down. Because, bless you, when you are accelerating, your displacement changes over time at an exponential rate. So since we're going from fast to slow, we're still faster at the beginning. We're still covering more distance until we actually end up slowing down. So we have covered half the distance in probably about a quarter of the time it's spent actually slowing down, which is why finding the time and cutting it in half is not my recommended technique.
got 107.6 because the 87, I got 87 from 88, not 88.78.
Oh, that's why my number's weird.
Yeah.
I put the 7 in the wrong spot. Thank you. Let me double check my own math then. Thought something felt weird.
772.
Thank you. Minus 3858.93. Square root of that number is, yep, okay, you guys were right. Thank you for letting me know. I got now about 62.16.
Yeah.
Does that feel better? Okay. You're not crazy. I'm just human. All right, so that is our angular velocity at this weird kind of halfway point. The last thing we're asked is how many RPM does that translate to? Why did I walk over here? I honestly don't know. An RPM is just a different measure of angular velocity, like the difference between meters per second and miles per hour. So we can pretty simply convert between the two. I've mentioned that your car probably has an RPM gauge, usually on the left side of the dashboard, and I certainly never use it, but if you do pay attention to it, notice that the numbers are pretty big. It tends to go up by steps of 1,000 RPM, whereas your speedometer probably goes up by steps of 10 instead. Because you can fit a lot of rotations in a single minute for a fast car. So we're going to convert rads per second into rotations per minute. We got radians at the top, so we will put 2 pi rad at the bottom to cancel those out. That will leave us with 1 rotation at the top. Next, we have seconds at the bottom, so we will put 60 seconds at the top of our conversion and 1 minute at the bottom. So to get to rotations per minute, we'll divide by 2 pi and multiply by 60. This will be a big number, at least bigger than the original number. Should be arriving at somewhere around 593.6 approximately. And RPM is the unit, because it does mean rotations per minute. You can write that as just RPM, capital or lowercase. You could write it as rotations divided by minutes. Notation isn't really a big deal. And that is this whole example from start to finish. How does this one feel? Weird? That's fair. Spinning things is weird, at least to our brains, which is used to thinking of things in straight lines. It's allowed to be, if you find it weird, that is okay. That is common. That's why I want us to do another one before we introduce anything new. Any questions? We'll pause for a second while I get some water and swap all the setup stuff on the board. Any questions before we break for a sec? Okay. The bathroom or water, etc. Now is a great time. I'll be a minute. I'm going to go ahead and write the preliminary stuff for the next question on the board. Bless you. Yes.
If I decided to try to figure out the time thing for the second part of the question,
Mm-hmm.
will I use the initial velocity?
Yes. I think you would still.
everything together, so it's.
No, that's fair. I've not done it that way, so I need to think about it for a sec. New. Okay, if we did this from the linear side, we knew acceleration, we knew the original velocity. If you knew half of the displacement, so you would still need to find displacement first, but we had the angular displacement, you could convert it to linear. Then you could find time. Alternatively, you could do all this with the angular variables as well. You know, half of theta, convert the original velocity into angular, convert the acceleration into angular. You could use that to find time. But, okay, yeah, you would specifically need to plug in that halfway displacement. And then the time would be that halfway time. But it would only be like, it'd be like 3/4 of the total time instead of half the total time. But if you had that time, you could put it, say, here.
Yeah.
So, doable, absolutely. Questions before we continue? Or concerns or confusions? All right. So, before we do the next example, I want to make you consciously aware of something you've observed before. And it has to do with linear versus rotational. Now, I don't advise riding a bike or a similar vehicle on a rainy/muddy day. But if you ever have, there's a particular issue that you might have encountered. Off the top of your head, what are the dangers of riding a bike on a muddy day?
It will not stop.
It will not stop, so it's hazardous to be on the bike in the first place. That's probably the worst thing. What is the most, after that worst case scenario involving not stopping and possibly falling, what is the not dangerous but inconvenient thing that can happen if you're on a bike on a muddy day? Sorry? Mud on your tires. And where might that mud end up? On you. So, cast your minds to this possible scenario that hopefully happens to you. You're riding along, and I'm going to consider this direction to be forwards for right now. You're riding forwards, there's mud on your tires. And whenever something is stuck to a wheel, or stuck to something that is spinning, it's going to have the same rotational data as the wheel it's attached to. It'll be moving at the same angular velocity, it'll have the same angular acceleration, it'll move through the same number of radians. And how that translates back into linear data will depend on the affixed object's radius from the center of rotation. In the case of, say, mud stuck to a tire, the mud will be attached and it will keep moving along the tire with that same angular data for as long as it's attached. The question, though, is what happens when the mud stops being attached? So let's track a piece of mud that's down here, it gets stuck, the tire moves along, and then at this point in time, it unsticks. Where's it going to go? What is it going to do? Kind of like this?
Yeah.
Maybe, possibly, actually. Now, once the mud isn't connected to the tire anymore, is it obligated to keep moving in a circle?
No.
No. All objects have momentum, and largely that momentum will tell them to keep moving forward in a straight line. The mud itself isn't the tire. The tire has an axle. The tire is compelled to spin for separate reasons. The mud has no inner compulsion to want to spin. Instead, it just wants to move in a straight line. And the most recent straight line it moved in pointed this way, in a tangent straight line to the edge of the tire. So, it's going to launch, if it lets go right here, straight up, and possibly onto your back, depending on how your bike is constructed and which wheel it is. Which is why, historically, most bicycles would have like a piece of metal splash guard over the wheel to help try to avoid that. Mine never did as a kid, though, because they were mountain bikes that weren't built to be ridden in the rain. Guess what I did anyway? And then I fell, covered in mud. So, the velocity with which it exits the tire will be the same as the linear velocity of the edge of the tire that whole time, because in the previous example, we treated the tire's linear velocity as the vehicle's straightforward linear velocity. Because specifically, for a wheel on the ground, its point of contact with the ground is a tangent point. It's only touching one spot, and the ground is, I guess, perpendicular, you can call it that, to the circle, tangent to the circle. So the wheel's linear velocity is the same as its tangent velocity, which is the same angular counterpart as its angular velocity. So whenever something lets go of a wheel, it will launch away at the linear equivalent of its previous angular velocity. And I hope you've never accidentally muddied yourself on a bicycle, but there's other places that you've definitely noticed this before. I'm assuming I was not the only kid on the playground that would do something like this, but if you think about like the metal, non-mechanized merry-go-rounds, not the big ones with lights and horses, the simple metal ones that you and your friends and possibly siblings would have to make spin manually and then you try to hold on for dear life. Yeah, I oscillated between points in my life where I was the big kid making it spin and when I was the kid hanging on desperately. And when you let go, when you eventually fly away from this thing, you don't fly straight out. Despite how it feels, you never come straight away. You get knocked to the side, because that's the direction your momentum was pushing you the moment you let go. If you've not done that, then there's another place, though, that commonly comes up. This is a rough diagram of the wheels inside of a pitching machine. So, baseball, tennis, etc. Usually there's one, I've seen them mostly with two wheels. It's possible maybe with one. Both of those wheels are spinning in opposite directions, such that if there's a ball between them, touching both of them, the tangent velocity it's moving at from both wheels launches it very fast in a very specific direction. So, much like how wheels spin in every vehicle you've ever been in, this specific linear to rotational back to linear phenomena has also occurred to you at some point in the past, I assume, or at least around you. And that's the case that we will use as our last example today. Yes?
So what makes, as far as the pitching machine go, what makes the ball, because you would think it would stay in a straight line because of the momentum, but what makes the ball rise or fall?
Usually a conveyor belt.
Okay.
Oh, you mean within the machine?
Yeah,
Okay,
I guess.
Usually there's some type of belt, or like there might be a conveyor belt that takes it up to this point and the wheels squeeze on it and launch it out. Sometimes if it's top fed, it might just be a tube delivering them
Okay.
down to this system. So it depends on the design, but there's
Okay.
some mechanism that will get it here, and usually the wheels themselves squeeze hard enough to get it in their grasp and then launch. Is that a question?
Yeah, is it like you're providing the ball with some kind of another momentum to increase its speed?
Yes, the wheels are imparting energy into the wheel ball, yes.
So we're still implementing the idea of that energy will actually start converting between things.
Yes, in this specific case, energy will convert from rotational kinetic energy into linear kinetic energy.
Okay.
So, rather than calculating into the examples that you've seen before, Dr. Rotacore came up with a much stranger example, and since I had to work this one when I'm a student, you guys get to as well. We're looking at the case of a grasshopper on a record player. Hence the weird drawing that I made a minute ago.
That's funny.
So, grasshopper is on the edge of this disc. The disc has a radius of 20 centimeters. We're just going to assume that the grasshopper is all the way on the edge as far as possible. Not any danger, because even if the grasshopper flies away from the disc, what bug has ever died from a fall? They'll be fine. We know the radius of this particular record. We know it starts at rest until some human comes over, turns it on, and sets it to the setting of 45 revolutions per minute. I don't know if you've ever gotten to play with a record player. I think I can count the number of times I did on one hand. But they do have a variable speed setting. Most of the records that you would play would mention meant to be played at this speed, but you could crank it up faster to make any album played by Alvin and the Chipmunks. I honestly think that's where the concept for those characters came from. We know this particular record will increase its velocity from 0 to 45 revolutions per minute over a period of 3 seconds. Note that several of these units aren't in the form we would actually use them in. For the simpler of the two, this needs to be meters. How many is that? 20 centimeters is 0.2 meters. Very good. Not spoiling anything, 0 revs per minute is thankfully going to be 0 radians per second. No need for math there. But we do want to convert 45 revs per minute into rad per second. I mentioned that mathematically revolutions and rotations are synonymous for right now. So this is basically just the inverse of the conversion we ended the previous question with. Cancel out revolutions, and put 2 pi rad at the top. And then we'll cancel out minutes and put 60 seconds on the bottom. And I believe that comes out to 4.7. Cool. I can remember things.
It's 4.7.
Thank you. 4.71 rad per second. And the first thing that we are officially asked to find is the record's angular acceleration during this 3-second speed up period. So we know disk radius, initial angular speed, final angular speed, and time, and we want alpha. With what we know and don't know, and the formulas, we'll put back on the board for convenience sake. No, back up, don't do that. What formula should we use for right now?
Okay, we use the simple one.
We can use a simple one. In fact, I recommend it. There's 3 things with alpha on the board. This will not help us right now because we don't know the linear acceleration. We also don't know time or displacement, so these 2 are out. Oh wait, we do know time, but we don't know displacement, so these 2 are out. That leaves us with the simple one, formula 2. So alpha, I'm going to rewrite delta omega as omega final minus omega initial over time. My omegas are devolving. It's a little better. Alpha will equal 4.71 minus 0 divided by 3 seconds. That should give us about 1.5 or something.
1.57.
Thank you, I can remember things. It's the 3rd time I've done this one this morning. All right, so that is the first part done. That's the angular acceleration of the record player for this first 3 seconds. Subsequent question, what is the linear tangential acceleration of the grasshopper while this is happening? As long as the grasshopper is attached, it's going to share all the same data based on its location on the disk. So all we really need to do is convert this into its linear counterpart. And we know the radius of the grasshopper from the center. So we can employ our nice straightforward conversion. So linear acceleration equals radius times alpha. It's going to be 0.2 times the 1.57 that we just found. Bless you. And by my recollection, that's 0.314. Cool. Yeah, 0.314. And that's linear meters per second squared. I don't think it's a coincidence that that is basically 10% of pi. Notice we're dealing with a lot of circles. All right, and that's part 2. So every second that passes, the grasshopper will become 0.314 meters per second faster, linearly speaking. And our last question is, if the grasshopper holds on for 5 whole seconds, what will be the speed at which it launches away at? Before we actually do that math, just quick concept question. If the disk is spinning clockwise and the grasshopper lets go right up here, what direction will he fly away in? Alright, a lot of people are pointing to the right. Fantastic. So, at this moment, this is the tangent line of the circle. And specifically clockwise will fly away that way. Now for the actual number, your first thought might be to employ 5 seconds and this acceleration in the linear version of this formula, which is not a bad guess. The one catch is, the problem tells us that at the 3-second mark, we stop accelerating. The angular speed topped out at 4.71. It didn't get any faster than this, which means that this will also be the grasshopper's angular speed the moment before it lets go, no higher. But that means that this is the number that we can just convert into linear form. You don't have to actually find a separate one. So, linear velocity is r times omega. So 0.2 times 4.71. And please correct me if I'm wrong, my memory puts that at about 0.96.
.942.
4.2, all right, thank you. And that's good old-fashioned meters per second. And we know what direction we'll be in, which is convenient. How's this feel? Nothing is good. If this doesn't feel good or intuitive to you, please do let me know, because if something confuses you, I want to know about it, because that means that I probably didn't explain it well enough and I need to revisit it. So as always, literally, if you have any questions, I want to know about it. That'll be it for lecture today. If you have lab today, I will see you there. If you have questions, please let me know. And otherwise, have a wonderful day and weekend.